stuff. And then we're going to go back to more quantum information-y, black hole information-y kind of stuff. I'm trying to set us up to be able to do some entanglement calculations. So that's kind of what I have in mind with all this CFT. But also it's just good old CFT. So the last part of what I want to discuss in general properties of CFT is two-dimensional conformal field theory. I've mentioned several times that 2 dimensions is different, and the reason for that is that in 2 dimensions the conformal group is bigger. In particular, it's bigger than SO D, 2, which would be the conformal group. So it's bigger than SO2, 2. The usual way to explain this is, of course, you don't need complex coordinates to do this, but that's what we like to use. So complex coordinates, z and z bar, with z is sigma 1 plus I sigma 2. Z bar is sigma 1 minus I sigma 2. And then you can think of, so you can either think of having these 2 real coordinates or 1 complex coordinate. A source of perpetual and never-ending and infinite confusion is that we are generally going to treat z and z bar as independent variables. Sometimes you have to worry about this and notice that they're secretly complex conjugates. That's important to get right answers and to know what you're doing. But when you manipulate equations, you can usually pretend that they're independent, and I'll try to be sort of careful about explaining how I'm doing that. The conformal transformations in a complex coordinate are very easy to write down. They're just z goes to z prime is any function of z, and z bar goes to z bar prime is a different function f bar of z bar. That is, we get 1 holomorphic function and 1 anti-holomorphic function worth of conformal transformations. Let's check that this is conformal. The metric under the replacement, z goes to f of z. The metric becomes df dz, df bar, dz bar, dz dz bar, which is proportional to dz dz bar. Now, I'm writing this arrow. This arrow means under the replacement. And this is one way of checking whether a transformation is conformal. Of course, when we do conformal transformations, we typically are not doing anything to the metric, although we can think of it either way. Infinitesimally, these transformations are z prime is equal to z plus an infinitesimal function of z, and similarly with bars. If we want to talk about, well, we can write a basis for these transformations just by writing a Laurent expansion. Epsilon of z is the sum of n from minus infinity to infinity, a n z to the n plus 1, and similarly with bars. So there's a bar n. To make this look more like the notation that we used in higher dimensions, where we had x mu and vectors and so on, this is x mu goes to x mu plus zeta mu, where the generators of the conformal group are zeta n, which is z to the n plus 1 d, and zeta bar n, which is z bar to the n plus 1 d bar. D means the partial, means the holomorphic derivative, and d bar is the anti-holomorphic derivative with respect to z bar. Okay, so let's count how many there are, because this is kind of confusing, and it has to do with this issue of the reality conditions and whether z and z bar are independent and everything. Okay, so first of all, let me tell you the answer. So there's 2 times infinity generators, okay? And what's a little confusing is that you might think that you have to set these to be real or something. But if you go back to real coordinates, so by 2 by infinity, I mean the number of real generators is, there's 2 sets of real generators with an index running from running over integers. One way to check that is to go back to real coordinates and preserve the reality conditions and you'll see that that's how many real generators you have. In complex coordinates, the reality conditions would set an bar equal to an star, where those are the expansion coefficients over there. But if we use complex language, the ANs can be complex. Okay, so we start out with 4 times infinity. We impose a reality condition, and we're down to 2 times infinity real generators. Okay, so the number of real generators is 2 sets of integers, of all integers. To understand the algebra, let's start by looking at the Lie brackets. So a Lie bracket between 2 vector fields, x comma y, L for Lie bracket is the Lie derivative along x of the vector field y. And it's easy to calculate this for these generators. I guess I should write the, okay, I hope I get the sign. I'm not totally sure I'll get the sign right, but the sign would be, or sorry, it would be x mu okay, I'm going to mess up the sign if I try to write down the Lie derivative, so I'm not going to. So if we plug in our generators, the Lie brackets of the holomorphic generators, zeta m, zeta n, give you minus m minus n, zeta n plus n. The Lie brackets of the anti-holomorphic generators, zeta m bar, zeta n bar, give you the same thing. And from this we can read off the conformal group, because it's generally true that the symmetries have to respect the well, let me write the formula and then I'll explain it. So in general, if you have space-time symmetries, the charges associated to those symmetries have to respect the composition law and therefore the algebra of the symmetries themselves. So in formulas, that says Q of zeta, Q of zeta prime, where this is now any vector field. I'm not specifying whether it's one of the holomorphic ones or anti-holomorphic ones, is equal to Q of minus zeta comma zeta prime. Sorry, switching notation here. Q of the minus the bracket. Zeta prime comma zeta. That's not quite true, actually. The way that you can see that this is required is by checking that the action of the charges is consistent with the composition law of the symmetries. But if you go through that, it's actually consistent to add a central term to the algebra here. So a central term just means a C number that shows up on the right-hand side, and that will appear in two-dimensional CFT, and we're going to find it shortly. Okay, any questions so far? So most of our discussion about 2D CFT is going to be a discussion about the stress tensor, because the stress tensor is, first of all, universal. It's in all CFTs. It's important. You can use it to calculate lots of stuff. And it's also just, there's a lot of information and a lot of interesting stuff going on in the stress tensor in a 2D CFT. Stress tensor is conserved.
Sorry, classically, is that the Poisson bracket? The commutator between charges?
Yeah, this, well, there might be some I's or something.
Okay.
If you want this to be a Poisson bracket, what I'm writing here is the commutator algebra.
Okay.
Yeah. So if you write the conservation law in dz bar coordinates, then it says d of t z bar plus d bar of t z bar is equal to 0. And the barred thing is, a version of that is also equal to 0. Now, if it's a CFT, then the trace vanishes. The trace in ZZ bar coordinates is the off diagonal guy TZ Z bar. Okay. So the mixed component, ZZ bar component of the stress tensor vanishes. And now if we go back to the conservation law, this one drops out, and we learn that T Z bar does not depend on Z. That's where the power of conformal symmetry comes in, that you get analytic functions, holomorphic functions. There's a different convention that's used in two-dimensional CFT. This is standard, unfortunately, so I'm going to use it. So let's define T to be minus 2 pi TZZ. T bar is minus 2 pi TZ bar Z bar. And big theta is 2 pi T ZZ bar. This is what people use in 2 dimensions for the most part in the literature. So this is the trace, and these are the other the holomorphic and anti-holomorphic components. And in this notation, what we just derived is that d bar of t is equal to d of t bar is equal to the trace is equal to 0. So that's the basic rule of conservation and tracelessness of the stress tensor in the 2D CFT. Sorry, I forgot to say something. So, okay, forget I said radial quantization for a minute. I want to talk about the charges now. Okay, so remember that the charges are Q of zeta is the integral over space, d sigma mu, t mu nu, zeta nu. And we have to choose what space is. So in order to talk about charges or the action of the charges, we have to decide what space is. Now, you might say, well, the charge is conserved, so it doesn't matter, but it's only conserved away from operator insertions, so it does matter. Usually in 2D CFT, we're talking about the charges as defined in radial quantization. So remember in radial quantization, we're working in 2 dimensions, we're working in Euclidean 2-dimensional space, which is R2, or the complex plane, if we want to think about this in terms of Z and Z bar. And space means the concentric circles around the origin with time running in the radial direction. Okay, so these things are space, and then the charges are denoted by L. So Ln is Q of zeta n, where zeta n is the generator that I defined a minute ago. And if we just plug in the usual formula for the charge, then another nice thing that happens in 2 dimensions is that this just becomes a contour integral. So this is 1 over 2 pi I times the contour integral dz of z to the n plus 1 t of z. Similarly for the bars, but I won't write them. Okay, so these are the charges, the conformal generators, the conserved charges of a 2D CFT. The fact that it's a contour integral of a holomorphic object means that you're allowed to deform the contour unless you hit a point where the integrand becomes non-holomorphic. And so if we have, say we have an operator insertion here, then you can deform the contour as long as you don't hit the operator insertion. But at the insertion, conservation is violated, T is not holomorphic, and you will pick up contributions. So we cannot, in general, just shrink this contour to the origin and declare this to be 0. It's going to be something non-zero, which depends on the path it takes around any operator insertions when you calculate some observable with this in. The inverse of this relationship just says that T of Z can be expanded in the Laurent series n from -infinity to infinity of ln z to the minus n minus 2. I've just inverted the contour integral. So the point is that the ln's are just the modes of the stress tensor. Okay, I would like to understand two things, mainly, in the next lecture or so. One is how the stress tensor transforms under conformal transformations, and the other is how the stress tensor behaves in curved space. There are many different ways of discussing this, and if you read books, you'll see every one of them. I've sort of picked my own route through this topic, which I find to be the easiest, sort of most complete way to think about it, but it's not what you'll see in most of the books that I know. I'm going to start by discussing what's called the Polyakov action. So the Polyakov action is the partition function in a curved background. So it's just the empty path integral with nothing in it, but in a non-trivial metric. And the way to think about this is that this is the generator of the stress tensor correlation functions. Okay, if I know z of g, then I can take derivatives of this with respect to g, and I can calculate all the correlation functions of t mu nu. So it turns out that in a 2D CFT, that's completely determined by symmetry, so we can write down this action in closed. We can write down this generating function in closed form. Recall in a curved background, we showed that big theta is minus c over 12 times r. Big theta is an operator. We showed this last time, I guess. So big theta is an operator. It's a trace of the stress tensor. And on the right-hand side is a C number, just the curvature of the background metric. If we take the expectation value of this in the metric G, then this is 4 pi by the definition of the stress tensor. This is 4 pi over root g, g mu nu delta g mu nu of log z of g. Okay, so this is a differential equation. This equaling that is a differential equation. And what we're going to do is we're going to solve that differential equation to calculate z of g. So our goal is to find z of g by comparing these two equations. We'll first do this in conformal gauge. So conformal gauge just means we set the metric g mu nu to be e to the 2 rho times the flat metric. And the anomaly equation, for the trace anomaly equation here, if we calculate R in conformal gauge, it's just minus 2 box rho. R is minus 2 box rho. So we get theta is the expectation value of theta is minus c over 6 box rho.
Not positive.
What? Oh. I seem to have a sign problem somewhere.
Not on the R.
I think it's here. Yeah. Which means that the variation means that under a Weil variation, that is a variation with respect to rho, the variation of log z of e to the 2 rho delta mu nu is well, in general, this is the trace, this is the integral of the trace, so this is integral d2z of root g of theta expectation value in this metric e to the 2 rho delta times delta rho. That's just the definition of the stress tensor. It's the thing you get when you vary with respect to the metric. Since we're varying with respect to the Weil factor, we're varying with respect to the whole metric, and that's why we get the trace here. Rescaling the whole metric, I mean. So if we use the anomaly equation, the trace anomaly equation here, and just plug it in, then we get minus c over 12 pi integral d2z sigma box rho. Okay, and that sign problem has come back. I believe this was supposed to be minus. We're going to end up with the right answer, so I think that means this has to be minus. Okay, so now we have just rewritten the anomaly equation as a differential equation for it's a differential equation for z in conformal gauge. That's what this says. Differential equation for z in conformal gauge. I'm going to switch colors. I feel like I'm shouting at everyone when I write in red. So we can integrate this differential equation. And it gives z of e to the 2 rho delta is equal to z of delta times exponential c over 24 pi integral d2 z of d mu rho d mu rho.
It's up.
Yeah.
What is sigma? What's sigma?
Sorry, delta rho is sigma.
Okay, yeah.
Yeah. Thanks.
What happened to the square root g?
I plugged in the conformal gauge. I plugged in conformal gauge here.
It
So,
should be square root JR equal to negative 2.
sorry?
It should be square root JR equal to negative 2.
Oh yeah, that's right. Yeah. Root GR
There we go.
is minus 2 box row.
Yeah, okay.
Thanks. Okay, so this is the answer for any metric in conformal gauge. This is the answer. Now, in fact, it's called conformal gauge because any metric in 2 dimensions can be put in conformal gauge. It's just a choice of gauge. It's a choice of coordinates. So, in fact, to find z of g, so the answer we're looking for is z in a general background metric. And to find z of g, we just need to find a covariant formula that reduces to what we found in conformal gauge when we go to conformal gauge. Polyakov did so, and he found the following formula. Z of g is z of delta times e to the minus s Polyakov of g, where SP of g, I'm going to write 3 equivalent ways. The first one is sort of mysterious looking. C over 96 pi, integral of d2x, root g, r, 1 over box r. I find this terribly not useful because it has the 1 over box in it. But people write it, so that's why I wrote it. Now let me tell you what that actually means.
I mean, is it suggesting that this is non-local or something?
Yes, it's definitely non-local. It better be non-local because, like, the stress tensor 2-point function is not 0. So the answer will be non-local. So what that formula really means is C over 96 pi integral d2x d2y root g of x root g of y curvature at x, g of x comma y, curvature at y, where this Green's function is defined so that box g of x comma y is equal to 1 over root g of x times the delta function x minus y. That's just what 1 over box means. You can see why it makes sense, because if I divide by box and plug it back in, I get back Polyakov's fancy way of writing it. Actually, an even more, so this is pretty good. You know, we can now calculate all stress tensor correlation functions. Let me emphasize what a crazy and wild thing that is. Okay, so in higher dimensions, we definitely cannot calculate all stress tensor correlation functions. That would be wildly difficult, impossible to do in an interacting theory. But we just did it in 2 dimensions. And this gives us a great deal of power over calculating stuff in 2-dimensional CFT. I'm going to write it a third way, which I think is more elucidating than this one. So the third way, this is equivalent, is we can write the Polyakov action as C over 48 pi integral d2x root g of x, a half d phi squared plus phi r on shell. Okay, so what I mean by on shell is that I've introduced a new field, phi. This is called the Liouville. This is called the Liouville action, and phi is called the Liouville field. Okay, so Liouville. So the thing we're calculating is a function only of g. And the statement is that you can get that function of g by introducing an auxiliary field and then plugging in its equation of motion. Okay, so the equation of motion is box phi equals r. So the statement is that if you introduce the auxiliary field and then you plug box phi equals r back into this equation, that's equivalent to Polyakhov's action. That's straightforward to check just by using this Green's function to solve the equation and plugging it back in. Okay, so the conclusion of this discussion is that we have this incredible action, the Polyakov action, which encodes all of the dependence of 2D CFT on the metric, and therefore tells you all correlation functions like this one in an arbitrary background. And all of these are determined solely by one number, which is C, the central charge that showed up in the trace anomaly.
Sir, this is calculating what? Just the connected correlators, or yeah, because it looks like the 1-point function would vanish if you do.
Let's see, why do you say it looks like, no, the 1-point function does not vanish. Why do you say it would vanish?
Okay. From that expression, from the
From this one?
The one before that.
From this one?
Yeah. Because it looks like I need to differentiate with respect to the metric twice to get something outside.
Ah, right, right. So you're right that the t in the flat metric will vanish. T mu nu in the flat metric will vanish, and that's correct.
Oh,
The stress tensor on the plane in a 2D CFT, the stress tensor on the plane has 0 expectation value. But as we'll talk about probably next time, you can also use this to calculate the stress tensor in a curved metric, and then it's certainly not going to vanish. A quick exercise that you can work through at home is to calculate the 2-point function in flat space from this formula. This is pretty quick, and it's worth doing this exercise. Maybe I'll put it on homework. And the answer that you'll get is T of Z, T of 0 in the flat metric is what you get by doing this variation twice. And this will give you C over 2Z to the 4th. One second. So not only do we learn T, we learned something new, a new interesting thing, which is that another way of characterizing the central charge is that it's the coefficient of the stress tensor 2-point function. Okay, so like, say I give you a theory like the free boson, integral dx dx, or dx d bar x. This is the free boson in 2 dimensions. And suppose I give you that theory and tell you to calculate the conformal anomaly. Well, the easiest way to do that is to look at the stress, is to just find the stress tensor 2-point function and read off the coefficient. And what you'll find is that it has c equals 1, which is, in fact, why we picked this convention for C. So if you remember, the way I introduced C was I said the trace anomaly was C over 12 times the curvature. Well, another way of introducing C is to say C equals 1 is that you read off the you look at the 2-point function of the stress tensor, and C equals 1 is the free boson, C equals 1/2 is the free Majorano-Weil fermion. And more generally, you can think of the central charge C as a measure of the number of degrees of freedom. So like 7 free bosons has central charge 7. Now when you have interacting theories, it's much more complicated and deep what do you even mean by the number of degrees of freedom. You can't just count the number of fields in Lagrangian. But in 2 dimensions, the right way to do it is the central charge. The central charge really is a measure, in every reasonable way, really is a measure of the number of degrees of freedom in a 2-dimensional CFT. Yeah.
I was still confused how we're going from SP to the correlation function. Is that related to the Green's function?
Oh, this is just, so the stress tensor correlation functions are basically, by definition, the variations with respect to the metric of log z of g. Okay, and we calculated log z of g. This is the Polyakov action. So, so the Polyakov action is the generating function for the stress tensor correlators. I've dropped some 1 over root g's in this formula. It's not quite right as written, but it's roughly right. Any other questions? Yeah.
Yeah, so this procedure looks quite generic, right? So what I think we have exploited the fact that the anomaly is one loop exact, so we can integrate the anomaly to get the generating function which is valid at all loop orders.
I have never discussed a loop here. I mean, what you're saying is true in what you're saying is true in a theory like free boson or whatever, but I haven't done any loops.
No, I was just wondering, like, why can't you generalize this procedure to higher dimensions? So that was my question.
Well, in higher dimensions, you can't fully integrate the equation.
Oh.
Okay, so in higher dimensions, you can calculate the trace on a Weil flat background. And you can extract quite a bit from that formula. Like, you can extract the stress tensor completely on homogeneous symmetric manifolds, and you can get a lot of information from it, but you can't, what you cannot do is write a formula in higher dimensions. You cannot write a formula for Z of G, purely from symmetry alone. Lots of pieces of Z of G are fixed by conformal invariance, but the whole function is certainly not. And that is basically the same as the fact that stress tensor correlators depend in higher dimensions, even in CFT, the stress tensor correlators depend on which CFT you're in, unlike in 2 dimensions where they depend only on the central charge.
And also, can we use this procedure in other areas in QFT? Like, say we have the Abijah anomaly and we integrate it, and can we generate correlation functions or something?
Sometimes. Sometimes. So, let me see if I can think of an example. I don't have a good example off the top of my head, but certainly you can extract some properties of current correlation.
Yeah.
Like when you have anomalous symmetries, you can extract some properties of the current correlation functions. I don't, off the top of my head, know of other cases where the anomaly completely determines everything for you. Like this, I'd have to think about that.
What information can you extract about the current correlation function?
Like in other cases? Well, the typical thing you'll find for like other global anomalies is that you can write down the right-hand side of this equation. So the anomaly is more or less telling you the right-hand side of the, so the current is not quite conserved. The anomaly tells you what's on the right-hand side. So in that sense, it's telling you at least this one-point function, but it also tells you how to evaluate this in other correlation functions. So you get some pieces of some of the higher like J with other stuff correlation functions, but I'm not really sure like whether I'm not sure if you get the whole generating function in those cases or not.
So you're saying you can write down a differential equation for the correlation function using the anomaly. Any correlation function which involves the current. Like something like a generalization of order identity. Is that what you're saying?
Right, yeah. So what usually happens, like in the things other that are not the trace anomaly, they usually have some, like chiral anomalies, this is what they look like.
Yeah.
So they tell you the divergence of the current. The right-hand side is a C number. So if you now plug this into a correlation function, you find that correlation functions don't quite obey the usual word identity, but they obey an identity that's just as powerful in the sense that you could still write down a word identity. It's just an anomalous word identity with an extra term in it coming from this C number, but it's often just as good. Sometimes it's even better to have anomalous. So there's a bit of a confusing thing, which is that often anomalous symmetries tell you more information than non-anomalous symmetries, which I always found a little weird. Like, if you have a symmetry, it seems like the best thing that could happen is that you have a symmetry. But no, the best thing that can happen in quantum field theory is that you have an anomalous symmetry. And it would take me kind of far afield to explain why, but it has to do with anomaly matching. That anomalous symmetries put really strict constraints on the effective action. And sometimes they're, in a sense, like more strict than actually having the symmetry. Because you have to match anomalies. For example, at different RG scales, the anomalies have to match because it's the only way to satisfy these anomalous word identities. And the matching of anomalies can tell you about things that are basically impossible to calculate any other way.
So can we interpret that form of the Polyakov action, like how we interpret in quantum field theory, where like you have some Goldstone modes when there's some symmetry which is broken and they get some non-zero action?
Yeah, I was wondering the same thing when I was preparing this. I'm sure people have thought about it, and I bet the answer is yes. So what we're talking about, the conformal symmetry in two-dimensional CFT is spontaneously broken. It's the SO22 subgroup annihilates the vacuum, but the rest of the conformal group does not annihilate the vacuum, so it's spontaneously broken. And I think it's probably true that you can think of this as the effective action for some kind of effective action along the lines of what you're saying for the spontaneous breaking of conformal symmetry by the vacuum state. I don't specifically know of a way to do that, but it sounds very reasonable.
So these are like really pseudo Goldstones then, because the symmetry seems to be explicitly broken, right? Because of Poisson, not just.
Well, I think you can think of this as the thing that, well, No, think of it as calculating the stress tensor correlation functions in the flat background.
Oh, okay.
Then I think there really is a conformal symmetry, and that's how I was thinking of it. But I'm not really sure. Maybe the way you said it is a better way to think of it.
There would be an infinite number of Goldstone modes, right? Because you had an infinite number of generators that you broke.
Yeah.
So where are all those Goldstone modes?
I don't know. I don't really know how to think about it that way.
Those
But
broken
you can't really
inductive
count.
things.
Sorry?
Well, they have non-trivial commutation relations.
Yeah, they're not. You can't count modes that way when you break a space-time symmetry with commutators like this. So I don't know how to think about it that way. It's probably a good way to think about it. I'll try to think about it before next time. Let's stop here.